Hello everyone. Today I'm going to explain the second study case of virtual works. Let's just get into it. So I have this kind of statement which is a consider cantilever beam of length L fixed at one end in point A and free at the other end on point B. So a point load P is applied downward at the free end point B. As a picture, as you can see on the screen. So use the principle of virtual works to determine the vertical deflection at point B. So I give you the given data, which is the length of the beam is 4 meters. For the load of P is 10 kilonewton, and I had this flexural rigidity of the beam is 200 times 10 6 power meter. So first, we assume that there is a virtual displacement. We see in here, there is a delta at point B, so delta B, right? So we already know that it happened because of an external forces. So if the virtual work done by the external load on P, so where is the virtual displacement is delta B. So we applied that this condition will be a displacement on force external equal to P times delta B. Okay, we agree on this. And if you see the visualization over here, that the cantilever beam on the moment of distance x, because there is a distance 4 meters, we have to transform the formula into this. Okay. Accent. Okay. Accent. Wait a second. Okay, the displacement equal to delta B per L X. Because there is a distance also for the movement from here to here. We don't know the distance, we call it X. Okay, after this, the internal virtual work is given by integrating the moment times the virtual curvature over the length of the beam. So we know that there is an internal condition. We're going to write it down over here. For the internal condition, internal condition, we use the integral L to 0 and M X. Okay, and in here, if you realize, this notation will be like this. Go up to delta B per L. Okay, because there's a curvature, the second derivative of the virtual displacement. Okay, the mx times to delta x dx, which is L 0 P on x delta V per L dx. Okay, so we have to evaluate this integral. How to evaluate this integral? Let's just continue in here. For internal movement, So delta B per L have P integral L 0 x dx. Okay, to solve this, let's continue. We got delta B for L P x to power per 2 L and 0, and then in here delta B per L P L L power 2 to power per 2, right? Okay, we use this kind of notation. All right, so it's equal to PL delta B per 2. Okay, now in here we got the notation. Next, we applying the principle of virtual work. In here, in new page, we know that the delta for displacement on X, for displacement on external, I am so sorry, external is equal to the displacement on internal forces. So P delta B in here equal to PL delta B per 2 that we already defined before in here, right? After this whole integration, and then we could simplify the notation. After this, we could use P delta B equal to PL delta B per 2. So solving for delta B P minus PL per 2 equal to 0. Okay, so 1 is L per 2 equal to 0. So delta B is PL 3EA. Okay, so after we got this notation, we substitute to the given values at the question in here. Wait a second, right? For LP and flexural rigidity. Okay, let's continue. So for the delta B equal to 10 and 4 okay, per 3 200 times 6 and every scan. Okay, so for delta B, 10 times 10 by 4 go to 64. 3 times 200 times 6 power. Delta B is 640 times 10 4 power per 600 times 10 6 power. So delta B is going to be 64 per 60, and then times 10 minus 2 power. So okay, delta B is going to be 1267 times 10 minus 2 and or 67 mm. Okay, so this is how we find out that there is a movement. Okay, there is a displacement in here on this cantilever beam. The x that we already find is 10 to 10.67 millimeter. So when the cantilever beam and has a fixed support on E, and given the external forces on P at 10 kilonewton, the displacement on B, we call it delta B, and the distance, the unknown distance is, we write in x, so we find the x is 10 something millimeter. So that's how we solve this kind of problem. Thank you for watching how I solve this study case. See you on next study case. Bye bye.